So the orbital angular momentum is L, and when L is 1, it is the category of the p orbital inside. Then the total angular momentum according to the quantum mechanics, we just need to remember that. I would like to calculate that. Is square root L times L plus 1. Then if you put L is equal to 1, then it means square root 2, square root 2 times h bar, the Planck constant. Okay, so this is the angular momentum. Let's draw it here. Alright, so if this is a nuclei, and consider it surrounding a sphere, and this is an electron here, and it is circling around, so it gives an L. Okay, so the angular momentum in the quantum world can be written down as a discrete number where L has to be integer. Square root L times the L plus 1 h bar. Okay. And we know that the electron is also spinning itself. Although this is not correct. If it is physically spinning with itself, then we have some problem with the general relativity. But that's okay. Here we just imagine it is spinning itself. Yeah, or we cannot proceed. Okay, so if it is spinning with itself, it also gives an S momentum. This is an L momentum and the S momentum. And with the same format, the total angular momentum with S equal to half for electron should be square root S times S plus 1 times h bar. Alright. So there's one phenomena called the spin orbital coupling. That means the coupling of the L momentum and the S momentum is put together in a specific configuration. So that gives you a new angular number called J. J is equal to L plus or minus S. So for p orbital, L is equal to 1, S is equal to half. So the total angular momentum will be 1 plus half, then it is 3/2. Or 1 minus half is equal to half. Alright. So if it is coupled, it has the same format of the angular momentum like this. And if the S and the L is in the configuration that satisfies another total angular momentum, then we call it coupled. That means we can see the L and the S was one thing, not two different things. Okay. So since the total value will be 15 divided by 4 square root, so this is all fixed number. So prefix number has a fixed configuration between them. So this is called the spin orbital coupling. When does this important? This important when one axis is different from the other. For example, if the axis has an electric field or magnetic field passing through that will make the spherical symmetry not spherical anymore. There will be one axis special to the other two. So you need to count it out, put it out, and that's the origin why if the spin and orbital is coupled along such axis, then the total energy will be further lower down. So that will split the P into J is equal to half of 3, or J is equal to half J is equal to half 3, or J is equal to half. If the J is equal to half of 3, then its projection to the A-axis have 2 different scenarios. One is its projection is 3/2. And the other projection is J is 1/2. So there will be 2 possibilities. For the J is equal to L minus S, the total angular momentum is half of 2 divided times half of 3. Then its projection back to the spatial axis has only 2 possibilities. It's equal to half or equal to minus half. So that recalls 1, 2, 3, 4, 5, 6 states for the studies. And for the study, so you have the 6p orbital, put it into 6 different states with different spin orbital coupling scenario. And these 2 are degenerate. So one band, second band, and the third band. So this is the origin of the heavy hole, light hole, and the speed of hole. For the conduction band, L is equal to 0. So there's nothing to couple. So no spin orbital coupling. So there's only one band in the conduction band, because it is the combination of measured by S orbitals. And for the p orbitals, if the spin and the orbital is coupled, and the J is equal to 3/2, and the MJ, the azimuthal projection, is equal to 3 plus or minus 3/2. These 2 bands, it is heavy hole. We call it heavy hole band. And because it is the effective mass according to the band structure is heavy, so we just call it heavy hole. Second, if the J is equal to 3/2 and the MJ is 1/2, then this band is light hole. The third band is that if the L is equal to 1 but J is smaller, the total J is only 1/2. The spin and the orbital canceling each other. Then and there's also 2 bands. This is speed of band. And because these 2, the MJ has the J is 3/2, and this is over half. So under the electric or magnetic field, this state has a different energy from the other 2. So that will split it from the band edge. That gives the spin a delta with a spin orbital coupling. Alright. So the heavy hole and the light hole, because the J is the same, under K is equal to 0, the energy is equivalent. Since the K is equal to 0, they are not function of K and the band edge here. So the top edge is the same. So it always drawing like this: one heavy hole, one light hole. If there's no any applied strength here, the most simple bulk case. If there's a strength, there will be light hole. Okay, and a third band always have a little bit smaller energy at the top. For gallium arsenide, the delta is 300 millivolt. But this number can be calculated or search on the internet to get a correct value anyway. So with the spin orbital, we know what's the origin of the heavy hole, light hole, and the speed of hole. If we look some book with certain depths, they will even show you how the combination looks like with the original central function. That's for the ux is the original central function based on px orbital. And the uy is the wave function according to the py orbital. Then heavy hole is the ux plus iuy. So this is purely mathematical linear recombination with 1 over square root 1 and I squared over square root 2. So it is just a linear combination. And you see that if you square it double, that will still equal to 1. Yeah, since that will be half of 1 over 2 plus ux squared plus uy squared. So that still go back to 1. So this is the normalizing constant. And the heavy hole with a bar at the top means it's the different speed. Because it's not included, the speed matrix is not included. So we only do the notation here. That means this is the one with different speed. If it is spin up, then this is the spin down. Same with the ux and the uy. Since the spin matrix is attached after the original wave function, but it's not written here. And normal people will not care about what the spin matrix looks like, so it's fine. We only need to know that first we put a bar to mean this is a wave function with different speed. Second, because the wave function with the bar is actually another wave function. So ui with uj, the bracket is delta ij. This is also true for heavy hole, light hole, and speedo hole, since they are all orthogonal. Yeah, you can try to practice or play with them by yourself. But if you have a bar here, one is spin up and one is spin down, it will still go to 0. So probably let's write it down like this. Ui bracket uj should be delta ij, and ui is still 0. Okay, so the spin up and the spin down, they are also orthogonal wave functions. So if you do the overlapping integral, you still get 0. It's because the attaching the spinner. Okay, that's you won't notice. With the other part relevant to spin, its integral is 0. It doesn't relevant to the wave function in space only. Anyway, you just need to notice that if two wave function with different speed, the overall integral is still 0. Since ux and uy have such relation, then you do the same thing. If you practice the same thing with heavy hole, light hole, and the speedo hole, it's a very clever recombination because these three functions still orthogonal to each other. So they are still 6 orthogonal bands. So such a relation still apply. Alright, so there's one important thing called the momentum matrix element. And momentum matrix element is a material parameter. It's just like how heavy you are. It's or what's the elastic constant of material. It's an inherent parameter. It's not something you could manipulate. Just like how tall you are, how heavy you are. It's a parameter of the material. And how does that define? Momentum matrix element, that means you do a expectation value of the momentum operator, Pi. If you remember that the momentum operator in the quantum world is minus I h bar gradient. So Px is minus I h bar d over dx. Py then equal to minus I h bar d over dy. Pz is the minus I h bar d over dv. Okay. Then what happens with the US? Pi uj. What happens? So let's fix I to be x. So I don't need to write it down every time. So okay. What does US? That. Okay, for convenience, we just let I to be x for convenience. So that will be US, the central band from the s orbital. Pi h bar delta x. And since I is equal not to j, so probably uy. Alright. Okay. And the y is equal to 0. Let's put the I bar out first. Minus I bar out first is US d over uy dx. Alright. So for u of y is original from Py. Py, the wave function is like this. So this is x, y, z. Okay, so it is something like this. Okay, so if you see along x, y, one is plus, one is minus. We flip back to the few pages before. And it is rotational along the y-axis. So uy deriving to bx is an even function over entire function. Oh, that's the chart. 正乘以，所以 you think 可以 du 这个 uy 这个函数对 x 做微分，你会得到一个奇函数。uy 对于 y 这一个轴，它是有旋转对称的，所以这一个函数对正 x 跟负 x 一样，所以它是一个偶函数。这个偶函数，一个偶函对 x 的偶函数，再对 x 微分会变成什么？会变奇函数。那 ux 是一个球状对称的函数，它是一个奇函数的偶函数。偶函数，所以偶函数乘以一个奇函数是一个奇函数。那奇函数整个积分得到的结果是0。好，所以 so if the I is not equal to j, then the overall integral should be 0. Although I don't know what the wave function looks like actually. Similarly, if we change the notation here, if we do the u of x minus I h bar d over dx u of x. Alright. So this is R to x. Even to x. Then times another even. Still even. Even. Okay. So the integral, at least we know something is not zero. And that's already enough. So and this non-zero value is the momentum matrix element of a material. Surely, if the material has a very pure symmetry, like x is not equal to y is not equal to z, then you have a free momentum matrix element. But for like gallium arsenide indium phosphide, the momentum matrix element is the set along free direction. So there will be only one momentum matrix element. Yeah, for like the in-game or out-game, they usually giving one number. Probably we only assume the growth is along the x. Yeah, or probably the momentum matrix along the x is also pretty similar. So it's usually only given one momentum matrix here. But there's indeed some paper that was try to calculate the different momentum matrix along different matrices. Alright. So now we have to introduce the parameter of the material. Since the UI and the UJ is the inherent property of a solid, is some kind of wave function. So this thing is important momentum metric, important material parameter as well. And it's listed like this. There's a sum from the textbook. Like for example, gallium arsenide is equal to 28.8 eV. If we times 2, then divided by its residual electron mass, you might be questioned why I write it down like this. That's because this form also appeared in the famous K.P theorem. But this calculation is based on the K.P theorem, a numerical method to try to evaluate the energy by the matrix presentation. Alright, so this is the answer, the final answer from the K.P theorem. That means 1 over NCZ, this is the mass of conduction band along the direction, is equal to blah 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 blah. Okay, so this is 1, and not equal to C. That means it's the interaction between non-conduction band. So EC is the energy of the conduction band. En is the energy, not the conduction band. So there's the three choices: heavy hole, light hole, or speed of hole. And you have the UC, PZ, UN square. This is a result of mass with the numerical method with metric expansion. Okay, this is something really I'd like to call it religional. 一种宗教，有点玄学。But anyway, that's pure science. But usually not very accessible for most of people. Anyway, we just follow the result here. So if we put UN to be the heavy hole, light hole, and speed of hole, one by one. So for the heavy hole and the light hole, EC and the En minus En is the band gap. After band gap. And the EC minus the speed of hole is the band gap plus a spin orbital, speed of energy due to the spin orbital coupling. Alright. So we can pull the M0 out. And a common term of this one as M n squared, because this is the definition of the momentum matrix element. So n squared out, m02. So now will be 2/3 Eg, because the 2 is due to heavy hole and the light hole, and 1 is due to the speed of hole. Then after some rearrangement, you're trying to pull out the momentum matrix to the other side. I think this is pure algebraic. You just try yourself. I'm not going to do that. It goes down to the m squared is equal to m0 divided by effective mass. So it is a universe value like the 0.0067, something that a universe value number here, minus 1. And another term with Eg and the delta times m0 here. So if we put the m0 to here and the 2 to here, that goes to the form of this value. And this value is in the term of, because usually this is the universe value. Energy divided by energy, also universe value. So the m squared times 2 divided by m0 is in the number of energy. Okay, and also relevant to its band gap. So it's relevant to its band gap and relevant to its effective mass. Okay, so now after some calculation, you will get some reported number here. And this value, if you either do that with calculation, if you have the band structure, you can calculate its effective mass. And if you have some the strong tool to calculate the speed of energy, yeah, it can be solved by theory. But the m squared is a material property that also can be experimentally measured. First, the effective mass can be of carrier can be assessed by cyclone measurement. Although it's also not something we're gonna touch in our department, but it can be made. The effective mass can be measured. It can be either calculated and be measured, and see does these two match. Second, if you have a proper excitation source and it's excited harder, you might get a 2 peak or 2 absorption peak from this band edge and the second band edge. So you can extract the number of the band gap and the delta. So the second term can also be measured. After that, you can measure this fundamental parameter of material. It's just like you can measure a density of a piece of iron by putting it in water and see how heavy it is and what's the volume that you can calculate. But if you have a very great tool to know its lattice constant and atomic mass, you can also calculate the density of a piece of iron. That's the same. That's the same reasoning. All right. So anyway, so this is also a number of we need to include first in order to calculate what the B12 is. Alright, so it's a rather long run. We make a short summary here. If atomic orbital, you have s orbital and the px, py, pz with the same energy in absence of external electric field or optical field. It is one s orbital and 3p orbital for one atom. Then you put so many atoms in lattice, one by one. Okay. Then the s orbital interacts then the total energy lowers a little bit. Also, the wave function, the shape of wave function also change a little bit, but the symmetry should be invariant, or should be very close. Then you get a US, the central function UX, and the similar the PXQRPZ gives you UX, UY, and the UZ. Then we added up the spin orbital coupling. Since for devices, we usually have some external electric field or optical field upon it. So the free equivalent band will further split into for the s orbital. This invariant. You just get still the same band edge, then with a parabolic approximation as a function of k. But the band edge of UX, UY, UZ will further split. 2 goes up and 1 goes down to maintain the total energy is not the same. I shouldn't do that. So the 2 level goes up, forms the heavy core and the light core, and the one further splitting down become the speed of core. That's the usual band structure of the all semiconductors.